Hi guys, I'm Aryan Agarwala. Welcome to our channel Learn Competitive Programming with CodeChef. Every week we upload tons of competitive programming related content, so here's a reminder to subscribe and click on the bell icon to stay notified. Today we're going to discuss a problem named burger which appeared in the May 2021 Cook-Off. This is an easy problem and it's ad hoc, so there are no real prerequisites. Let's take a look at the problem statement. You have taken an eating challenge from chef and now you have to eat exactly Y burgers. You will eat in the following way. In the first minute you will eat exactly X burgers, and every minute after that you will eat exactly twice the number of burgers you ate in the previous minute. Since you can get tired of eating, chef also allows you to take a break for exactly 1 minute. When you start eating again after taking a break, your eating streak resets. That is, in the first minute after the break, you will eat exactly X burgers, and every minute after that you will eat exactly double the burgers you ate on the previous minute. Let A1, A2, AK be the length of your eating streaks in minutes. Chef requires that all AI are pairwise distinct. Find the minimum number of minutes you need to eat exactly Y burgers, or determine it is impossible to do so. So in our input format, we're given t test cases, and in each test case, we're given two integers x and y as defined in the problem statement. Alright? In our output, for each test case, we need to output either the minimum number of minutes required to eat exactly Y burgers, or -1 if this is impossible. The constraints are t is between 1 and 10 to the power 5, and x and y are between 1 and 10 to the power 18. Okay? So we're looking at something like order of log x or something per test case. Okay? Okay. So first we're going to jump into the problem and make some quick observations. So first, let's analyze what an eating streak looks like. Okay? So in an eating streak, at the first minute, we eat X burgers. Okay? Then on the second minute, we eat 2X burgers. Third minute, 4X burgers. And this goes on until at the ith minute, we have 2 to the power I minus 1 X burgers. Okay? You see that, right? Because on the first minute, we have 2 to the power 1 minus 1, which is 2 to the power 0 burgers, which is 1 into X burger. Okay? Then on the second minute, we have 2 to the power 2 minus 1, which is equal to 2 into X burgers. Similarly, on the third minute, we have 4X burgers, and this continues until on the ith minute we have 2 to the power I minus 1 into X burgers. Okay? So, in total, on an eating streak, we have these many burgers, right? We add them all up. So, it comes out to this. Let's say we spent k minutes on this streak. Okay? So, the number of burgers we eat on the streak are this. Right? And if you take the x out, you can write this. Now, this is just a property of powers of 2. Like, there's no explanation behind it. You can prove it by induction if you want. But it turns out that this is just equal to x multiplied by 2 to the power k minus 1. Okay? The property, to be exact, is this, that summation from I is equal to 0 to k minus 1 of 2 to the power I is equal to 2 to the power k minus 1. And you can take some examples, right? Let's say k is equal to 4. Then we have 1 plus 2 plus 4 plus 8, which is equal to 15, is equal to 2 to the power 4 minus 1. Right? Good. So, what we have shown is that in an eating streak, of X minutes, we consume this is small x, by the way. So we consume big X multiplied by 2 to the power small x minus 1 burgers. Okay, Now, our total eating pattern will be divided into multiple streaks, right? So let's say there are total k streaks. Okay? And to be consistent with the terminology used in the statement, we'll say A1, A2, dot dot dot, AK. Alright? Now, the total number of burgers consumed, let's call it BE for burgers eaten, will be the summation of the burgers consumed in the individual streaks, right? So that will be x multiplied by 2 to the power a1 minus 1 plus x multiplied by 2 to the power a2 minus 1, so on and so forth until we get x multiplied by 2 to the power ak minus 1. Alright? And if we just take x out, we can see that this holds true. Okay? I've just rewritten this in some mathematical terminology. Okay, to make it easier for us. So this is the number of burgers eaten. Alright? And now let's calculate one more factor, which is the amount of time taken to eat these burgers. Okay? Now, on each eating streak, we spend AI minutes, right? A1 minutes, then A2 minutes, so on and so forth. And then in the middle of two eating streaks, we have to take a break for 1 minute. So we add a +1 here. Okay? And this keeps on happening till the end. So in total, we have k minus 1 plus 1s. Alright? So the time taken is equal to the summation of the k's, ai, sorry. So this is the amount of time taken on eating streaks. Okay? This is the amount of time taken on eating streaks. And plus k minus 1. So this is the amount of time taken on breaks. Okay? Now, we want an eating streak such that the number of burgers eaten is equal to y, where y is given as input. Okay? And we want the time taken to be minimized. Okay? In this in this eating pattern. Okay? We want the time taken to be minimized. And they want us to output this minimum time. Okay? Now, to do this, we'll make some observations. So we have BE is equal to y. Right? So, we have x into this right? Yeah. Now this is equivalent to writing this. Right? We just divided both sides by x. So now we can see that if y is not divisible by x, answer is -1, right? Because if y is not divisible by x, then this side is not an integer, whereas this side will always be an integer, right? So y is not divisible by x, answer is -1 straight away. Okay? Now, so for now, let's replace y. So we'll check this, and then we'll write y is equal to y by x. Okay? Y divided by x. So that's why instead of writing x on this side again, I'll just write y. Okay? So we have this condition here. Okay? Now, this is equivalent to saying right? So over here, the minus 1 was inside this summation. Okay, so over here I've taken the contribution of minus 1 in total, so it's minus 1 multiplied by k, which is minus k, and I've taken that outside. Okay, so then we can say this. Okay, okay, now this is useful. Okay, and why? Well, it's useful for this reason, that chef requires that all AI are pairwise distinct. Okay, so this is the sum of distinct powers of 2. Alright, and there's a very good way of interpreting this, which is in binary. Alright, so let's say we have 2 to the power 2 plus 2 to the power 4 plus 2 to the power 0. Okay, in binary. Actually, 0 doesn't make sense here, does it? So let's say 2 to the power 3 in binary. Okay, how would that go? Well, in binary, the representation would be simply 1 1 1 0 0. Okay, and so this requires a good understanding of these number systems, I suppose. So these are the corresponding positions, right? Okay, now why exactly does this help us? It's because each number has a unique representation in binary. Okay, and so if we're saying that both of these sides are equal, then it means that this, like all these AI, are representing the binary version of y plus k. Okay, so that means that y plus k can be written uniquely in this form. Okay, in this summation. So what we're going to do to get our answer is, we're going to iterate over all of the possible k. Alright, and I'll show you that all of the k are actually small, but for now it's like they can be as large as you want. Okay, so we iterate over all of the values of k possible. Okay, obviously k is positive. Alright, and we check what's the binary representation of y plus k. Okay, now the binary representation will be something like this form, right? This is just a random number, I haven't used any pattern here. Alright, and all of these numbers will have a position in binary, right? So this will be the first one, this will, or rather this will be the 0th one, right? Because it's 2 to the power 0. This will be the first one, second, third, fourth, fifth, and sixth. Alright, now we're going to note down all of the positions which are set to 1. Okay, and let's actually invert this a bit to make it easier. Okay, so we're going to note down the positions which are set to 1. Okay, so this is set to 1, this is set to 1, this is set to 1, and this is set to 1. Right, there are 4 places that are set to 1, and the places are 1, 2, 3, and 5. Okay, so there are 4 places. Okay, and the set is 1, 2, 3, and 5. Okay, so first note that our equation is working here, right? Because 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3 plus 2 to the power 5 is equal to this number here, y plus k, which we represented in binary. Okay, so let's say that it has n places. Okay, so what we want is that k is equal to n, right? And that's because here the number of AI have to be equal to the thing we added, right? So we have that k has to be equal to n. Okay, and if k is equal to n, then we have a valid configuration which we can use. Okay, so how do we use this configuration? Well, you have to realize that the number of places here, or rather the set of places that we found, so we saw that the bits 1, 2, 3 and 5 were set. So that set 1, 2, 3 and 5 corresponds to the set A. So A1 is equal to 1, A2 is equal to 2, A3 is equal to 3, and A4 is equal to 5. Okay? And so to get the amount of time taken, we can use that formula we found, right? This formula here. So the formula is just the sum of AI, so that's 1 plus 2 plus 3 plus 5, so that's 8 plus 10 plus 11, so 11 plus k minus 1, so 3. Okay, so 14 here. Okay, so this is the amount of time taken to complete this kind of eating streak. Okay, so the idea is that we'll try this for all k, and we'll simply take the minimum of the time taken across all k. Alright, now to show that k can't be that large, this equation itself is actually enough. So let me write this again once neatly. Yeah, okay. So you just have to realize that this side grows very fast compared to this side. Okay, so the minimum possible sum we can have on this side, if we have k different terms, is like 2 to the power k minus 1. Okay, just take my because okay, don't take my word for it, because we can have this side be equal to something like 2 to the power 0 plus 2 to the power 1 plus dot 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 2 to the power k minus 1, which is equal to 2 to the power k minus 1, right? The same property we used above. Alright, so let's just write it as this. This is not 100% accurate, right? Because this 2 to the power 0 wouldn't be there, but it's more or less correct. Okay, is equal to y plus k. Alright, so we need 2 to the power k is equal to y plus k minus 1. Okay, now y is in the range this, right? Which let's just write as, okay, this is more or less the range. So that means 2 to the power k is equal to 2 to the power 60 plus k minus 1. And okay, again, just for ease, let's do this. Okay, so when k is equal to exactly 60, we see that oh, we can try this for both extremes if you want, by the way, but this is just easier because the larger y is, the larger k can be. Okay, so for this 2 to the power 60, you see that let's say k is equal to all the way up to 60. Okay, because this has to be positive, right? K minus 1 is positive, so this also has to be positive. So k has to be greater than equal to 60, right? So let's say k is 60, then this is equal to 0, right? Let's say k is 61, okay? Then this is equal to 2 to the power 60. Okay? And if k is 61, then we already have that 2 to the power, so let me write this clearly, 2 to the power 61 minus 2 to the power 60 equal to 61 minus 1. So we have 2 to the power 60 equal to 61 minus 1, which is already too big, right? And the bigger k gets, the more absurd these terms will become. Okay, so that's why k ends up being pretty small. So we'll just check for k in this range. Okay, yeah, so just to be safe, we'll check all the way up to 62. Okay, and yeah, let's look at the code then. Okay, so we start by taking an input here. Okay, which is the number of test cases. Then in each test case we input x and y. Now y mod x basically tells us if y is not divisible by x. Okay, So if it's not divisible by x, then we output -1 and we continue. Okay. Otherwise, we divide y by x and move on to the rest of the code. So first we say found is equal to false. Okay. So this basically tells us if we have an answer or not. Okay. So if we don't, then we'll output -1 at the end. Okay. And this basically stores the smallest possible answer. Okay. And 189 is just a huge amount. Okay. Like the answer will definitely be smaller than that. So now we'll check for all k. So I wrote k in the explanation. I've used I here. Okay. So we can think of I as k. Okay. So we're trying for y plus k, right? Now we go over the binary representation of y plus k. Now this term here basically tells us that is bit j there in y plus k. Now if the bit is there, then we increase the count of bits. Okay, so I wrote this as n in my explanation. Okay, and ta is basically storing the time taken. So I wrote this as tt in my explanation. Okay, so if this bit is set, then it means that we're doing an eating streak of a to the power j. Okay, sorry, we're doing an eating streak with taking time j. Okay, so to the time taken we're adding j. Okay, you can think of it as writing ai equal to j, that kind of thing. All right. So once we're going through the done going through the binary representation, then we'll just check if is count equal to I. So remember I told you that n has to be equal to k, and count is equal to n, and I is equal to k. Okay, so we basically check is count equal to I. Okay, and if it is, then we say answer is equal to minimum of answer and time taken for these ai plus count -1. Okay, so this is the time taken on breaks, and this is the time taken in eating streaks. Okay, and we say found is equal to true because we just found a possible answer here. Okay, so now if we haven't found an answer, then we say answer is equal to -1, and we just output the answer at the end. Okay, so yeah, we can try to submit this. So as you can see, we have the correct answer here.